Now we entered into time dependent rheology. Time independent rheology is your plastic, pseudoplastic and dilated flow. Now we are going to enter into time dependent rheology. First topic in that is thixotropy. I'll be very fast. Listen. Why I am explaining thixotropy again? Because whatever the rest is there, it is connected to that. Okay. So what is thixotropy is, you have polymer in water. Polymer will sit between the layers of water. We have multi-point of contact. Multi-point contact. When you shear, polymer will align in the direction of flow. So, what is that? Contact break. It is gel. This is salt. After some time, again it will regain its original position. Gel salt gel conversion is thixotropy. What is happening here? I'll be very quick. Listen. You add gum to water. You add gum to water. We have imaginary layers of liquid. Okay. We have imaginary layers in the liquid. You add gum to water. This gum will go sit between the layers. It will attract the water molecules and it will swell. Due to this, it will cause resistance to flow. Hence, it is in gel form. Multi-point contact with the water. Gel form, multi-point contact. You took sauce. Sauce is in gel form. Multi-point contact. When I hit it, this multi-point contact will break. That sauce gel is converted to salt. That is the reason it is coming out from the bottom. After coming out, it will fall on the, what is your favorite? Samosa. Okay. It will fall on the samosa. After falling on the samosa, it will not slip. It will stay there. Why? Again, it will gain back its multi-point. Okay. Again, it will gain back its multi-point contact. Sir, you told us sauce and samosa example where it is used pharmaceutically. I want to develop sustained release injection. Sustained release, how we do is, we take drug, we add drug in the polymer. Now drug will take time to come out from the polymer. Drug will take time to come out from the polymer. Take drug, add polymer to the drug. Take drug solution, add polymer to the drug solution. Your drug is entrapped in the polymer matrix. So assume this as a drug. Drug is entrapped in the polymer matrix. Now drug has to come out. So we have so many molecules here. Slowly one by one molecule will come out. This is called sustained release. So I have an injection, solution form. To that injection I will add polymer. I get gel. Okay. Now how you give gel to as an injection to the patient? For that you need to incorporate thixotropic property. For that you need to incorporate thixotropic property. So when you add this gel in the injection, when you press, initially in the injection it is in the form of gel. When you press the injection, the gel will lose the contacts. Contact will break. Okay. With whom the contacts? Water. Gel will lose the contacts and also the polymer will align in the direction of flow. It will not restrict the flow. Instead of restricting the flow, it will align in the direction of flow. It will align in the direction of flow. Due to this, the thickness or gelling property is reduced. So it is easily coming out from the injection. See, the needle is very small. So it has to come through the needle. So if you incorporate thixotropic property, it will come through the needle. Once the injection is given, when it enters to the muscle, again it will gain back its gelling property. Now, your sustained release is only come into picture when it is in the gel form. Remember, not in the sol form. When it is in the gel form. After giving injection, again it is regaining its gel property and it will release the drug slowly. One injection is enough for 2-3 days. So it will give the action for 2-3 days. That what is your sustained release formulation. 1. 2. I want to formulate suspension. Suspension, if it is flocculated suspension, I want the particles to be suspended. Okay, so I will add thixotropic property. How to add thixotropic property? What is the material you are going to add to gain thixotropic property? Polymers, because thixotropy is a property of pseudoplastic system. Thixotropic is the property of pseudoplastic system. Example for pseudoplastic is polymer in water. Add polymer to the suspension. Now initially it is thick. I want to redisperse it. Initially the suspension is gel form, not that much gel, somewhat. It is thick. When I shake the suspension, it is converted into sol. All the particles are distributed. All the particles are distributed. First, again it will come back to gel. When it come back to gel, the particles remain suspended for 5-10 minutes. So within 5-10 minutes, you have to take out your dose, have it. So this thixotropy is also useful in the suspension, emulsion and injections. We use this thixotropy in suspension, emulsion and injections. That what is your thixotropy. Next part of time dependent rheology is bulge. We'll speak about that. Okay. Better we speak negative thixotropy because you will understand easily. See, the graph for thixotropy is so your pseudoplastic will start from origin. I will shear it, leave it aside, again it regain its consistency. Again I will shear, regain the consistency. Shear, regaining. You need to represent where it is a up curve and down curve. What we call this loop has, I told the name, hysteresis loop. Hysteresis loop. This loop is called as hysteresis loop. This is your thixotropy. Remember, thixotropy, the graph is moving towards left. Graphic moving towards left. I told you why left. I need to apply only less pressure to get more. It is shear thinning system. It will become thin, thin and thin. Next is negative thixotropy. Obviously, how will be the graph? Towards right. Towards right. What is the example? What is the example, madam? Magma, bentonite, magnesia magma. How much percent? Not given. Okay. Magnesia magma. So what is there? Why it is gaining the consistency? See, this one is, listen, take gum, add gum in water, you get the gel, take the gel, start rubbing once. the gel will lose its gel property. Again, so much loose. Again. Lastly, you find only small thing. All the gel property is lost. That what is thixotropy. This one, magnesia magma is a suspension of a magnesium. Magnesia magma is a suspension. In the suspension, we have deflocculated, more deflocculated particles and less flocculated particles. More deflocculated. Hence, this is thin. Okay. Hence, it is thin, less viscosity. When I apply shear stress, when I start rotating this magnesium magma, take it in a beaker, start rotating the magnesium magma, due to your shear stress, they will collide with each other and they will form more flocculated suspension this time and less deflocculated suspension. Due to this, it will become thick. Leave it aside, it will go back to original position. More deflocculated and less flocculated. You need to write here, more deflocculated, less flocculated. Here, more flocculated, less deflocculated. Here again, more deflocculated and less flocculated. You got what I am saying? See, listen, don't write, listen. I have deflocculated magnesia magma suspension. Initially, it is very thin. When I start rotating it, due to my shear stress, the particles of magnesia magma will collide and start forming floccules. Due to floccules, their movement is restricted. Okay, its consistency will increase. Movement is restricted, consistency will increase. If I remove the shear stress, again these floccules will break and come to the original position. But this time, if this is 100, if this is 10, this will be 50 and this will be 15. This time its consistency is increased. In thixotropy, consistency is lost. Here consistency is increased. Next time again you do it. See here. First time I increase, its consistency is increased. I left it. Again it is coming back. This whole one loop is this one. The one loop from here to here, going up and coming down together is this one. I will explain this here. Initially we have deflocculated suspension. When I stir it, it forms flocculated and its viscosity increases. Next, when I leave it back, slowly it is coming back to original position, but this time it has increased viscosity than the origin. This is origin, than the origin we have increased viscosity. Second time if I rotate, it will start from here. Again, when I leave it back, it will gain the viscosity. So here it is 15. Now second time I will start with 15. It will end to 25. Then 25. It will end to 35. So on it increases. This what is negative thixotropy. Because it is behaving dead opposite to thixotropy, hence we call it as negative thixotropy. Bulges is also a thixotropy. Bulges is also one thixotropy. Listen, why the name is given bulge? Something is bulging there. What is bulging? See here. What is the example, madam?
Concentrated aqueous magma gel of weight 10 to 15% by weight.
(10 to 15% bentonite gel). Listen, don't write, please listen to this. This is the up curve, this is the down curve. If you take 10 to 15% bentonite, start rotating it, you will feel so much resistance due to this bulge. What happens there is, bentonite is a clay. It is in the form of crystals like this. So crystals are individual. Initially, crystals are individual. When I start rotating, these crystals will form house of cards like this. All crystal will sit on each other. Due to this, more resistance to flow. This resistance to flow comes in the form of bulge. More resistance to flow. So it will come in the form of bulge. This is called bulge. Sir, why we are studying? By any means in your formulation, because you are a formulation scientist, in your formulation, if you are adding 10 to 15% bentonite, your machinery will be gone. If you rotate with fast, slowly you have to increase the speed. If you rotate fast, due to bulge, machinery will break. Okay, slowly. So you need to plan how to rotate. That is the reason why we are studying this. So what is bulge? In the rheogram, this is called rheogram. Or what is another name of rheogram? Consistency curve. Rheogram or Babu. Rheogram or consistency curve. In the consistency curve, because you are getting bulge, hence we call it as bulges. We call it as a bulges. Bulges is also thixotropy. Why it is a thixotropy? See, going up and coming back. It is regaining and losing the viscosity. Regaining and losing the viscosity. Hence, bulges is also considered as thixotropy. Right somewhere. Important GPAT question. Is bulge is a thixotropy? Yes. Then we have spur. Name is given because we have spur-like projection in the rheogram. This is called spur. Spur is also thixotropy, remember, because we have up curve and down curve. Somewhere you write down, this is also thixotropy. When is the next class? 12. Okay. See, last class is 1 hour. You saw the timetable? 12:10 to 1:10. Only last class is 1 hour. I made it 1:10, they changed it. I kept break for 20 minutes. They added this break for 30 minutes. Break is for 30 minutes, but we initially kept for only 20 minutes. We assume that you are getting vada paos and eating it within 5 minutes. Okay, listen. Shh. It's a joke. Okay. Shh. Procaine. G means gel. G means gel. Procaine, penicillin, G. It's an injection. Okay, listen. When I am sharing, procaine, penicillin, G, initially I will face so much resistance. If I still steer, suddenly all resistance is broken. Suddenly all resistance is broken. See, if you understand what I am telling, concept, you can draw the graph by yourself and you can write that concept also by seeing the graph. Initially I am giving the shear stress. I am feeling resistance. So it is going rightwards. Remember, in the rheogram, if you go towards right, more resistance, towards left, less resistance. Initially, I am feeling so much resistance. At one point, even though I am feeling resistance, I am rotating. At one point, suddenly I will feel no resistance. Why? Because there will be structural breakdown. There will be structural breakdown. Your procaine penicillin G structure will suddenly break. Hence, its viscosity is reduced. Initially, I will face more viscosity. Suddenly, I will face less viscosity. Why I am facing less viscosity? Because its structure is breaking down. Structure is going to break down. That what is your spur. Why we call this as spur value? What is the why here? Indication? Okay, spur value y. Okay, sir, what is the use? Sir, what is the use? I said you here, you need to concentrate on your speed. Here, if your spur value is more, that injection will act as more sustained release. It will stay, it will form depot and it will release the drug very slowly. Okay, if you want your injection to be act for 3, 4, 5, 6 days, if you put here, it will form depot. From that depot, it will release slowly. It should not melt down. To create such type of injections, you need to take an material whose spur value is more. If spur value is more, it will stay there for more time and release the drug slowly for more time. So that what is your thixotropy, negative thixotropy, bulges and spurs. Another small topic is there, rheofexy. Rheofexy. It's not that much important. Listen, rheofectic material, initially it will be like liquid. If you just shake it, it will convert into gel. That's all. A slight shaking is enough to convert to gel. Tell me what is given there. Read it out. A gentle.
Rheology is a phenomena in which a salt transforms into a gel state more readily rather than keeping a solid at rest.
Next.
Gentle shaking or low rate of
Okay.
shear.
Listen. Rheofectic materials are those materials, initially they will be liquid. When I just shake it, suddenly convert into gel. Suddenly it will convert into gel. But that type of rheofectic liquids are not much used in the pharmacy. We don't use that much. Okay, suddenly it will be converted into gel. Okay, your dilatant flow is also a type of rheofexy. What happens in dilatant flow? It is shear thinning or shear thickening? Shear thickening. Dilatant flow will become thick. This one is also becoming thick. So both are same. Remind me in the lab, I will show you dilatant flow. I told you na, you can walk on the water. I'll make you to walk on the water. Just we need to add something in the water. That's all. I'll make you to walk there. If you stand, you will be drowned. If you walk, if you run, you can run on the water. So we try to see that. That is due to dilatant liquid. Same thing is for rheofexy. Remember, rheofexy and dilatancy is same. Okay. Rheofexy you need to shear more. Dilatant no need. Just little shaking is enough to convert it into gel. That what is your rheofexy. Rheofexy, little shaking is enough to convert it to gel. Dilatancy you need to increase your shear stress continuously. That what is thixotropy. Then measurement of thixotropy. It is there in your syllabus? Check. లేదా మళ్ళా క్వశ్చన్ వస్తే అవుట్ ఆఫ్ ద సిలబస్ అంటారు. నో, టెక్స్ట్ బుక్లో ఏముందో అది చదువుదాం. Measurement of thixotropy. Listen. First method is measuring the area of the graph. Take the graph of thixotropic material, measure the area. This area will give you the thixotropic breakdown. What is thixotropy? Is that particle is combining or breaking down? కంబైన్ అయితే విస్కాసిటీ ఎక్కువ ఉంటుంది, బ్రేక్ డౌన్ అయితే విస్కాసిటీ తక్కువ ఉంటుంది. థిక్సోట్రోపీలో విస్కాసిటీ తగ్గుతుందా పెరుగుతుందా అంటే కంబైనా బ్రేక్ డౌన్? బ్రేక్ డౌన్. రిమెంబర్, హెన్స్ వి కాల్ ఇట్ as థిక్సోట్రోపిక్ బ్రేక్ డౌన్. ఫస్ట్ వన్, graphical method. Draw a graph of thixotropic material, measure the surface area within the loop. Measure the surface area within the loop. That will give you an idea of thixotropic breakdown. Second one, increase time of shear. Third one, increase rate shear stress. First one is graphical method, second one is increase time of shear, third one is increase shear stress. Listen, see here, listen to me carefully, otherwise you will miss out. I will shear, listen here, don't write, listen, everybody please listen here, see how I am drawing the graph. I will shear for first time, maintain the same shear stress for time t1. See, first time if I shear and leave, it will come back here. I will maintain the same shear stress for time t1, again it will come back. Second time I will shear, this time I will maintain this time for so much long, again it will come back. T1. Listen, what I am trying to tell you is, so I am shearing first time. Okay, while shearing, I will maintain the time. Instead of shearing for only 2 minutes, I will shear for 5 minutes. Okay, and I leave it back. So, first time I sheared only for 2 minutes. Second time I sheared for time t1, 5 minutes. Left it back. Third time I sheared it for time t2. Leave it back. Measure the slope. Slope of t1 is 1 by u1. Slope of t2 is 1 by u2. Plastic viscosity. Okay. u1 and u2. Now by using formula you can find out the thixotropy. Tell me the formula, madam.
V is equals to
Hmm.
u1 minus u2 by
Natural log t2 by t1. By using this formula you can find out what is thixotropic breakdown. Did you understand this? Only I am changing the time. ఒకటి 5 minutes చేశాను, ఇంకొకటి 10 minutes చేశాను అంతే. 5 from here to here 5 minutes, from here to here 10 minutes. Just I am changing the time. Just I am changing the time. Listen, this time, can anybody guess the graph? Not you. Anybody guess the graph? అంటే ఫస్ట్ స్లోగా రొటేట్ చేస్తా, సెకండ్ టైం ఫాస్ట్గా రొటేట్ చేస్తా. సి స్లో రొటేషన్, సెకండ్ టైం ఫాస్ట్ రొటేషన్, స్లో రొటేషన్ అండ్ ఫాస్ట్ రొటేషన్. స్లోగా రొటేట్ చేస్తే చిన్న లూప్ వస్తుంది, ఫాస్ట్గా రొటేట్ చేస్తే పెద్ద లూప్ వస్తుంది. రెండు డౌన్ గ్రాఫ్ యొక్క స్లోప్ తీసుకోండి, రెండింటిది డౌన్ గ్రాఫ్ యొక్క స్లోప్. వాట్ ఇస్ ద ఈక్వేషన్ మేడం?
U1 minus
న్యాచురల్ లాగ్.
V2 by V1.
V1, this is V1, this is V2. V1 is rotating at slow speed, V2 is rotating at fast speed. I repeat once again, listen, I will stop here. How to measure thixotropy? Graphical method. Draw a graph, measure the area. Measure the area, that will give the idea of thixotropy. Okay. Case 1 small area, case 2 small big area. Which is having more thixotropic property? థిక్సోట్రోపీ అంటే ఏంటి? లూజ్ అవ్వడమా, గెయిన్ అవ్వడమా? లూజింగ్ ద కన్సిస్టెన్సీ ఇస్ కాల్డ్ థిక్సోట్రోపీ. ఇదొక ఏరియా ఉందా? ఓకే, ఇదొక ఏరియా ఉంది. ఎక్కడెక్కడ లూజ్ అయింది? 1 2? Obviously 2. So by measuring the area, now you are finding out where the thixotropy is more. So that what is first method. First method is graphical method. Draw a graph for thixotropic material, measure the area. Then you can tell this. Next is increase time of shear. First you rotate for 5 minutes, then you rotate for 15 minutes or 20 minutes or 10 minutes. Then you will get this too. Measure the down curve, not up curve. Thixotropy is very very important for down curve. Down curve yokka, sorry, measure the slope of down curve, substitute in this below formula, you will get thixotropic breakdown. Next, shear stress. Okay, what I will do is, initially I will rotate with 1 velocity, second time I will rotate with 2 velocity. So by taking this I will get the graph. In the graph for the down curve I will measure the slope value, y2 minus y1 by x2 minus x1. That is substituted in the formula to get thixotropic breakdown. Okay, to get thixotropic breakdown. That what is your thixotropic measurement. You will stop here.